Hi, welcome to the Bronte site. This is the location where we'll be doing our mapping and logging assignment. The first thing we need to look at is safety. So number one, we're on a cliff face, so keep away from the cliff. There is no reason for you to approach the cliff. There's no requirement to do it, so I don't want to see anyone over there. If we look behind, there's a lot of cuttings, rock cuttings. Stay off the rock cuttings. You do not have to climb any rock faces, so stay away from that. When we're down on the road, there are vehicles, so you must wear a safety vest. So if you could please visit the 4th floor office where we'll be able to lend you a safety vest. It's a boomerang, please return it. But please be wearing your safety vests. When you're down there, always work as a team, work as a group, always have somebody that's in charge of safety that is standing back, looking for vehicles, warning your own group as well as any other groups in the vicinity that there's a vehicle, and also keeping an eye out above and around you, as you should as well. Always be looking, considering your safety. Are there unstable rocks, etc. around me? Here there shouldn't be, but get in the habit of doing it every time. The other thing you should do, we're very exposed as you can see, so please put on sunscreen, wear a hat, much like I'm not doing right now. So after that, we can get started. Having looked at the geology map, what we know is that we're in, or should be in, RH Hawkesbury sandstone. If we look around the site, what we can notice is that we have long, extensive, thick layers, what we call beds, of yellowy, grey, reddish coloured rock varying around. This is the sandstone. If we have a look in detail, we can see the grains, and those grains are visible, but less than 2 millimeters. So that falls into our sand size. So if it's predominantly sand-sized particles stuck together, we have sandstone. The next thing we can look at is focus in, and we can see that it's sort of a shiny white color or clear color. That's the quartz cemented with silica. So quartz cemented with quartz. Again, matching what we learnt from our geology map. So we know we're in sandstone. Then we can look in detail, and we might see within our bed some features. So if we look at this bed over here, we can see a pattern in it. We may not see that in every rock, in every layer, but in this bed we can see that pattern, which we call cross bedding. The cross bedding is formed when it was still a sand. So this Hawkesbury sandstone was deposited in rivers, and in this case the flow would have been in this direction, and the sand was being deposited in little sand dunes by the water, by the fluid. And so the sand topples down and creates a pattern on this angle. Since then, all this material has been compacted by masses of layers above us that have been now eroded. So it's compacted, cemented together by the groundwater, bringing minerals that cement the grains together, forming or lithifying into sandstone. So this pattern is our cross bedding. It is not a defect. It does not form a break. Occasionally, and we'll see a number of them when we do a mapping in the cutting, they do form a break, in which case they're now a defect and we need to map them as a weakness plane in the rock. But initially here, none of this pattern is a weakness, it's just an intact rock descriptor. If we're looking for the weaknesses, the first thing we note in Hawkesbury sandstone, we've got the layers. Now between each layer is a time gap, a period where we don't have deposition. Those are the bedding planes. So the long continuous defects are our bedding planes, and these are a major feature of a sedimentary rock. Within the beds, if we see a break, much like a crack through concrete, so if we see a break through the rock, that's a joint. So a joint is a break through the rock. It's often rougher than a bedding plane because it's not a tensile feature. But it's also a lot shorter. So it might be confined to a single bed or maybe 3 or 4 beds, but won't be much more extensive than that. If we're thinking about the regional model for Sydney and sedimentary rock, then we need to consider that we're in a basin. And if we're in a basin, we'd expect all the layers, those beds, to be sloping slightly to the middle. The middle of the Sydney Basin is roughly to the west of the Harbour Bridge. And so if we're to here, the southeast, then our layers would typically be dipping slightly to the northwest. So we need to have a look at that and see if that model is matched by what we see on the site, because we may have local deformations that may change the dip. The ground I'm standing on here is a bedding plane. So if we look at this bedding plane and follow it around, we can see that it's roughly planar as expected, slightly undulating. If we look in the distance, we can see that the bedding planes are quite extensive, extending across a number of bays. We also notice, if we can look at the footpath over there, that it's dipping to the northwest, exactly what we would expect from a model in a basin. So I think we can confirm that this is part of that regional model and that we can assume that's correct. When we're on a site and we're looking at geology, we would really want to develop a three-dimensional understanding of what we're looking at. So it's really important that we don't just stand in one spot. What we want to do, walk around the exposure, filling our head with an understanding of what's going on. So let's have a walk and look at some of the other aspects of this site. If we view this section of rock, what we can see again is the bedding planes, sub-horizontal, and then within each of the beds, again, we can see the cross bedding, and in this case, some of them have formed weakness planes. Now, these weakness planes are dipping towards the east, so the bedding, roughly sub-horizontal, the cross beds dipping to the east. We need to remember this when we're down in the cutting and we're viewing the wall of the cutting. Okay, we've now come down into the rock cutting, so your job now is to identify the site you've been allocated. These will be based on the car parking numbers, so you'll be given 2 or 3 of those car spaces as a method of giving you a sampling window, where you will then map the defects in the rock within that sampling window. The first thing to do is remember that if we're going to be looking at a rock mass, we need to stand back and get a large overall picture. So think big first, move into detail. Never start with detail, because you move in, you start measuring things, you measure things that aren't important, and you miss things that are important. So if my site is on the other side of the road, I'll stand on this side and look at get an overall picture of my face, rock face. So when I'm looking over there, I'm going to look at that face and look at it in the context of what we've seen before. So if we remember before, we've got bedding planes. Within each bed we might have cross beds, and then breaking through those beds we have joints. The joints being like the cracks in concrete, breaking through some beds. We remember that the bedding planes should be sub-horizontal. That's what we saw before, and it should be the same here. So keeping those in our head, then we look at the face. So the first thing I notice is we've got long continuous bedding planes of the sandstone that we saw earlier. So that matches what we thought. What's unusual here on this corner is that I can see some features that look like a syncline. They look like curved defects. We didn't see those before, so it doesn't make sense. What these really are those cross beds we saw that were dipping to the east, and they were planar. The reason it's misleading here is that we're on a bend and we're also on a road that's dipping downhill. So it makes it look like it's a curve. But all of these are orientated that way, so when we're recording data like this, we need to make sure that we record it as cross beds in that orientation. The other features we can see are the joints, so we can see various breaks through the rock mass. What we want to do with these is move around, so don't stay in the one spot, move around and look for different joints on different orientations within your sample area. One of the things we do want to do is see if we can identify joints that are similar. So if I find one, I'll move along the site and identify another one that's parallel and similar. Those two then are part of the same defect set. A set of defects is a group of defects with similar characteristics. So I can identify each of the sets. This enables me later on to create or regenerate a model of my rock mass by adding in each of the different sets. So stand back, look at my face, Identify the major defects of interest, so the bedding planes, the cross beds, the joints. Choose the ones that seem to be having most impact on the rock mass, and now we'll move in and measure those. All right, so we've stood back from the face, we've identified the major defects, now we're going to move in and measure some. So let's just choose this one as an example. This one here is dipping on this direction out towards the coast, so it's one of those cross beds that we've seen a couple of times. There's a number of them, so it's part of a defect set. There's one here, one there, and they continue up through that bedding, that bed. All right, so what we want to do now is we want to measure the orientations of the defects. What I might do first of all is just look at the defect, put the clipboard here, or if there's not much face to see, then we'll put the clipboard, line it up so we can measure on something. So roughly in the direction of the dip, we might have an estimate of the dip. It's always a smart thing. So this is dipping towards the coast, so roughly east, so roughly 90. The dip's the angle from the horizontal down. So if we're measuring the angle horizontal down, then that might be 15, 20 degrees, something like that. So we have in our head a rough estimation so we don't make a mistake. If we ended up with a dip of 90, well, that would be vertical, so that's clearly not right. Horizontal is 0. Remember the difference, we go from 0 to 90, not more. So if it's 100, it's actually 80 in the other direction. So we've got in our heads an estimate. Now we'll measure, so we put our geological compass, or in this case an iPhone with an app which you can get for free. Put that on here, measure the dip and dip direction. So I can read off that this is roughly 18 degrees dip, 109 dip direction. And that roughly matches what our guess was. So we're happy, that's reasonable. Remember, our dip is always 2 numbers and our dip direction is 3 numbers. Once we've got the orientation of the defect, then we have to measure a few other characteristics of the defect surface or the defect plane so that we can actually estimate properties for them later on. So the first thing we'll do is an easy one, is the length. Now you need to measure the full length you can see. Don't restrict yourself to the window of observation. So if you've been given a 20-meter window, the defect can still be 100 meters long. It's whatever you can see. So measure the length. The next thing you do is you look at the termination. So what happens at the ends of the defects? Do the defects continue? So in the case of a bedding plane, they're likely to just keep continuing. So you'd write CC, continues on both ends. Or does the defect terminate on something? So a cross bed will terminate on a bedding plane. So you might have 2 bedding planes on each end. Or a joint might terminate on a bedding plane or another joint. So note what defects the defect surface you're measuring terminates on. So 2 letters for terminations, you can make up your own system. The next thing we want to do is we want to measure spacing. So this again is about the rock fabric, how broken up the rock is. So here we've got spacing. Now it makes no sense to measure spacing between 2 different defects. So if we have a bedding plane and a cross bed, well clearly they'll meet at one point, so that's a 0 spacing. And if you keep going the other direction, it goes to infinity. So it makes no sense. So the only spacing you do is between similar defects, defects of the same set. So here the spacing would be from this one to the one parallel to it. We can move our board along to make sure it's parallel. So that distance there. Normally we will use an average. So if I was measuring this one, I would go the average from this to there and from there to there. And that gives you the spacing for this one. We do that for each of them, and that way we get variability across our defect set. The next thing we want to do is we want to get characteristics of the defect surface. So we can stand back and look at the overall shape and get a rough shape of the defect. We can get variations of the plane, so from the plane of the defect. So all we've done is measured plane of best fit. So what about the variation? So we can get what we call the interlimb angle. the angle between the bumps on the defect. So this is the large scale, so imagine the defect has a wavelength to it. What's the angle of the bumps and how far apart are those bumps? What's the wavelength of that defect? When we zoom in, we're interested in how rough the surface actually is. So we look at a surface of about 100 millimeters scale, and we're considering how rough it is. There's a number of different methods to do it. So you might be comparing it, say, to rough sandpaper or a smooth surface, or you might be copying profiles or comparing to different profiles like the Barton profiles. All right, so we've measured the roughness in different scales, which we can use to estimate friction angle. The next thing we want to do is to look at the opening of the defect. So if we have a wide open defect, it's clearly a lot lower strength than a closed defect. Also, an open defect means there's potential for groundwater to flow through there, either now or when we're doing whatever engineering project we're doing. So we can look here, and what we do is we get what we call the aperture, the average opening of the defect. We also describe what's in the defect. So in this case, it's clean. So we might say it's clean. Or we might notice the reddish orange staining, which is the iron oxide, the iron staining. So we might say iron oxide coating or iron oxide veneer. Or we might see clay in there or soil, and we describe the clay or soil using soil mechanics terms. So what's in the defect, how thick the defect is. The other thing we want to do is identify how much moisture is coming out. It gives us an idea later on in our engineering project about potential for groundwater flow through your rock mass. So here it's dry. I don't see any evidence of water, so I'm just going to write dry. Other locations we might see evidence of water has come down, we'd mark that. Or we might see water, it's damp, moist, flowing, etc. Just describe what you see coming out of the defect, if anything. Also note the weather of the day and the month, because that will also impact how much water you see on the surface. All right, so once you've done all those, you can move to the next major defect that you've identified from the other side of the road. The other activity you need to do at the site is to create a site description and a site plan. What I want you to do is act like geotechnical engineers. So it's not just a plan where you show a road and where the buildings are. You actually want to add in details that are helpful to a geotechnical engineer, that help indicate if there are issues with the subsurface, or tells us what might be below the ground. If we have a look around, some of the things that I like on your site plan, definitely topography. So you might be able to put in contour lines if you know those, but also put in some measured slope angles. So for example, the road, you can measure the dip or the slope of the road, always measured in a downward direction. Over on the grass, measure that. Up here, so measure different slope angles, put double arrowed vectors on with the slope angle on your plan. Look at some of the engineered features. So if we have a look at the road, what's the condition of the road like? Is there any damage to the road? If there is, just hatch in where the damage is. Look at the gutters. The gutters are made of concrete, they're a brittle material. So if there's any subsurface movement, that would be indicated by cracks in the concrete. Can I see any cracks in the concrete? If so, where are they? Mark them on the plan. In this area here, you will find cracks in the gutters. That's mainly because the expansion gaps are too wide apart, so they're broken in between. But in other sites, it might be because of ground subsidence or landslides or something like that. Look for other features of importance. So groundwater is very important to us. So can you see any areas of seepage? Can you see any plants that like being in water all the time, sort of boggy type plants? So further around, if you're looking at the face, you'll see an area where there's water seeping out almost permanently. So you would mark that there. Before they redid the road, below that water area, all the pavement was damaged. So it would have correlated with where you marked in damage to the road. So mark those features. Look at other engineering features. So if you look at the buildings, what condition are the buildings in? How old are they? Look at the retaining walls. Are they still vertical or are they tilted over? So record information like that as well. Vegetation, what plants are there? Where are they? Where's exposures of soil and rock? So put those into your site plan. That will make it a much more useful tool when you go back to the office and you're trying to make a model of what's going on at the site. Well, that's all from me, so the rest is up to you guys. Remember, come down, work as groups, remember safety, keep safe, we want you back again. And don't get too stressed. This is all about getting out in the field, having a go, learning a few new skills. I look forward to sitting down in a Bronte cafe marking about 100 of your assignments, but in the meantime I'll be going for a surf, so I'll see you later.